Again, welcome to this Pipeline Industries Guild webinar. This is part of our 2020 Guild Awards programme, and today I'm delighted to welcome Wez Little and Andy Killer from ControlPoint, who are going to provide us with a presentation on their award-winning artificial intelligence inspection of electrofusion for PE pipelines. This won the Land-Based Onshore Technology Award for this year. So I think that's all from me at the moment. If you can use the chat function, if you have any questions during the presentation, and then I will host a Q&A session at the end of the webinar. So I'll pass over now to Wez to start the presentation. Thank you.
Okay, cool. Thanks. Hopefully everybody can hear me. So my name's Wez Little. I'm the commercial director for ControlPoint. I've got Andy Killer, who's one of our senior developers. And we're going to talk to you today about the development we've done for artificial inspection of electrofusion of polyethylene pipelines. We were really honoured and quite humble to win the award. And what we're going to go through today is really a bit of an understanding about the background to why we moved towards artificial intelligence, but also a bit about how the artificial intelligence actually works, which is why I've got Andy, who's our in-house expert, on how it actually works in reality. So it should be a really interesting topic, hopefully, for everybody. So I'll get started. You have reached a monumental point within your life. There are some classic examples there of things that have occurred in history, and today's webinar could well be as insignificant as walking on the moon, winning the World Cup, the invention of the iPhone, or more like Peter Kay would say, we believe that the AI is the future, no longer is garlic bread the future. ControlPoint, where we're not a fittings or pipe manufacturer. We don't provide equipment, but what we are is we're passionate about electrofusion or polyethylene insulation quality. You can see there a lot of things that we provide in terms of training and education, and really we set about being passionate about your network. So we're looking to eliminate poor practices, uncertainty, and ultimately eliminate leaks on plastic pipes. In terms of how we've broke that down over many years around the issues associated to electrofusion quality. Have you muted me? Can you hear me?
Yeah, I can hear you, Andy.
All right, okay.
It just went quiet for a moment.
All right, okay, cool. So in terms of what we've discovered over the last decade, really, is that quality is not really a puzzle. In effect, there are a number of ways to address quality concerns that we see within the networks. Data capture is one of those, remote inspection, analysing and looking at the data mapping, testing, on-site support and training. Those are the kind of things which we believe allow asset owners and contractors to truly say that they've got a quality control system in place. In terms of electrofusion, this is important to understand why we've developed the AI in the way that we have. Poor practices do not provide the following. Poor practices do not provide the right kind of clamping, the right amount of scraping, and often do not mean that joints are assembled in a controlled manner so that there is no issue with contamination. What we believe and what we can evidence and prove is that actually education, controls, monitoring will achieve a right first time approach, and we've got many examples from many clients that have been able to do that. Because everything we do is driven by data and the data that we've collected over many years, This is a simple but hopefully effective pie chart to show to those on the call that what we found, these are the most common causes of electrofusion joints, whether that be for the water or gas sector, failing early in life. And by early in life, that means anything that really fails after, say, 50 years, or in the water sector, it's believed that polyethylene will last for 200 years. So you can see there that the three largest causes of electrofusion joint failure are misalignment, contamination, scraping, and then there's a quantity of others where that could be weld wipes or things that down to fitting failures, etc. And in the right-hand side, there's two images. One is a top tee, electrofusion top tee on gas that has failed, and it's failed in what we would call a brittle manner. And a simple way of explaining that, don't want to assume people know everything about electrofusion joints, is if you imagine a Kit Kat bar, if you bent it, it would snap. That would be classed as a brittle failure. If you were to take a caramel-filled bar and bend it, it would always pull out, and that would be classed as a ductile failure. So that joint, the top tee, has failed early in life during during service, and it's as a result of the electrofusion process not being completed fully. You can see where there is a brittle failure between the two surfaces. The bottom one is a oldie but a goldie from previous ones, where that joint was flagged for issues around assembly, contamination and clamping, and it failed after 4 months, taking 500 houses off water and somewhere in the region of £100,000 plus in terms of cost and damage to the network. What we like to do is show that there are quite large risks around electrofusion joints failing, and it's the reason that we want to eliminate that. So I'm just going to show this next video. There's no sound, but this is a video footage taken by CBS from an explosion that occurred in the United States, in Harlem. What you see in there on the screen is a low pressure electrofusion socket weld failing in the basement of the building. And the washout on the right-hand side is not where the explosion occurs on the left-hand side of the screen. So this is a low pressure, largest diameter main that failed. Unfortunately, 8 people lost their lives as a result of that. Following lots of investigations by various US government bodies, it was found that this was down to poor preparation and poor practice. So you can see the impact of a large-ish diameter electrofusion explosion, and as I say, mindful that this would be what we would consider to be a low pressure setup. As the video progresses, you'll see the physical scale of devastation that it's caused to the building. Hundreds of people were left homeless as a result of this explosion. There's a few interviews here. I've kept the sound off because they're just basically saying it felt like a bomb going off or an explosion. You can see there the remnants of the building that remained. And hopefully this will start to give you a feel for the reason why we believe AI allows us to eliminate this before a weld even takes place. In terms of the things that we see happening on sites around the UK, these are examples of photographs that we have received from people who are evidencing the work that they are doing. So on the one on the left-hand side of gas joint, you can see there, in order to cope with the coiled pipe, they are using a plant digger bucket to hold the equal T down. They've already scraped the outlet and buried it in mud on the other side. We'll have to hope that they will clean that appropriately before assembling it, but these are the type of things we see. On the right-hand side, we can see there's evidence of post-scraping as a result of breaking through to the black on the co-extruded. There is no presence of a clamp, and there is significant contamination. Given that those three things alone are the primary causes of early life failure, it's the reason why we wanted to move towards an AI solution for quality control. People often ask how we get the data. We have a truly integrated approach to collecting data from electrofusion boxes. We've spent many years developing apps, and thankfully since the advent of clever or smartphones, we've been able to use those to our best advantage. And this short animation just shows you the way that we collect data. So inside pretty much all Electrofusion boxes in the UK, there is a Bluetooth chip. Once it's controlled by our app, you can then scan the fitting details to enter onto the box the correct weld time and the traceability. It then allows you to take photographs of your image. So one from above showing the clamp, one from the left-hand side, and one from the right-hand side showing that it was clean, that it was scraped. The operative can then review the photographs before sending, and once they've sent the photos, the box will begin to weld. If the weld doesn't complete, alerts will be generated. Assuming it does, then we collect the data from the box. So we get the weld time, all of that data around barcodes, locations, photographic evidence. We even get the weather condition as well. And we then uplift that data into the cloud so that we can basically then use that information to give a client an indication of whether or not that joint is or isn't conform according to their own standards. Once we get the information back, we would have a human, and we're not saying we're going to get rid of all humans with AI, so nobody needs to worry that we're turning into that horrible Terminator-style film where robots are taking over the world. But a human will then inspect the joint and the photographs to look for what we would consider areas of concern or risk around how a joint's assembled. A client selects their own risk appetite, and then we alert based on that appetite. So you can see there that we'll send out a mobile phone notification to the welder and to their supervisor so that they can determine whether or not they wish to have that joint buried or remove that joint before it is backfilled. All this is done post-weld. So the photographs are pre-weld, but the decision or the inspection currently comes post-weld on most of our clients. We know that the apps or our apps are excellent from a behavioural tools perspective, because typically we would assume on the photos that I have shown you that no one has maliciously created a poor joint. A lot of it can be down to education, awareness, access to the right tools and equipment, or the challenging environments that they work within. But again, what we do see where clients use them is that the app allows you to drive towards a much more conformant level of installations. And it's one of the areas that specifically is targeted by Ofwat in the water sector is around leakage of assets, in particular new assets. So you can see there, this is an example of a client from 2013 who used the app and went from slightly over 35% good joints under their own scheme. So this will be in accordance with Wez 43208, right through to how they ended up probably, just over 18 months later, where they are pretty much putting in every single joint is a good joint. There'll always be, for some clients, 10% that may need some rework. And really what we think the AI will allow us to be able to do is address for those clients that are using the system, or address for any client really, that last 10% of uncertainty. So why did we decide to develop artificial intelligence? I'm pretty sure that Andy, who sat with me, has asked that question of himself on a number of occasions. Because we know that our system works. There's enough evidence to prove that our system works. But what we were looking to achieve, or what the team wanted to achieve, was a pre-weld inspection. They wanted something that was truly responsive in terms of speed. We wanted to change the right first time analogy to right first time every time and prevent rework, the loss of fittings as a result of poor preparation. But ultimately, our mantra has always been to eliminate poor preparation and leakage on networks. So before I hand over to Andy, really what we set out with, because everybody should have a vision and a goal when they start these type of projects. For many years, I've been involved in the innovation space. And the vision was to build an artificial intelligence electrofusion inspection system to eliminate joint failure. Visions are always quite woolly, often aspirational. But really, we had a very clear goal in mind, and that's what's kept us grounded through this development that we've done ourselves. We wanted to build a system that can give instantaneous control of joining practices. And that's what we've set out to achieve. Now, I'm going to hand over to Andy, and Andy's going to take you through, quite slowly, the process of developing an artificial intelligence system, because we're surrounded by these systems in everyday life that we now take for granted, that we don't actually see as being artificial intelligence. So Andy's going to take you through the next section and hopefully give everyone a really good insight. It was even useful for me during this week and the generation of this to learn about what AI is and what AI isn't. Andy.
It's sort of a brief introduction as to what AI actually is. Now, obviously, everybody here will have heard about AI. Everybody has probably used AI. But I think if you asked anyone to actually describe to you what it was, or perhaps to try and explain how an AI learned, maybe not everybody would have much of an idea as to the answer to that. So let's start with the sort of definition. So you've probably all heard of the terminology for artificial intelligence, but there are also some other descriptions that you may or may not have heard of. Now, these include machine learning and deep learning. Now, if you look at the sort of circle diagram to the right, you'll see that these are all kind of subsets of each other. So artificial intelligence is the main root science, and then machine learning is a part of that, and then deep learning is a part of that again. And what you find is the sort of further in, or the deeper you go, the more sort of information you're able to abstract and the more complex the systems get, but equally the better overall result that you end up with. So if we move on to this next slide here, this is a definition for AI. So AI, as it happens, was actually developed in the 1950s, and it was described as any technique that enables computers to mimic human intelligence. Examples are using things such as if-then rules and decision trees. Now, at this point, maybe this might sound quite complex to people, but you will have all done this without realizing. So a classic example would be an email rule. So here's an if-then logic example. So for example, here I have an Outlook rule that says, if an email comes in from Wez, I want to move it to the Wez folder. Now, this is almost as basic as it gets, but you are in effect here teaching your computer. So you're telling it, when this happens, I want you to do this action. And similarly for us at ControlPoint, we actually use decision trees in our joint inspection process. So here's an example of that, where we obviously score joint records. We give a percentage value as to how good or bad or conformant and non-conformant we believe they are. Now, our inspection team aren't manually typing in those numbers. We derive it by effectively following a flow chart. So they're asked several questions along the way, and depending on which paths and turns they end up making, we end up with either an X% or a Y% or a 0% result at the end. And again, this is probably something you may have also all used yourselves. Now, that is the sort of definition of AI, but it's quite basic and quite limited. And then next we have machine learning, which was one of the subsets from before. Now, machine learning was invented in the 1980s, and it's described as a subset of AI that includes techniques that enable machines to learn for themselves and improve at tasks with experience. So now this is all about getting the machine to understand and to learn, rather than for us just to program it. An example of machine learning that, again, you will have all used, hopefully, is Royal Mail. So between 1987 and 1991, they developed and installed 46 optical character recognition machines, or OCR machines. And these were designed to scan envelopes and scan the addresses on the envelopes, and then be able to automatically extract the address information and therefore aid with the sorting process. And quite interestingly, apparently each of these machines was able to process roughly 30,000 items of mail per hour, which back in '87, that seems quite impressive to me. And so obviously at this point, I guess hopefully your next question may be, well, how did they actually teach this machine to do that? Now, the example I'm going to give, it may or may not be the same as how Royal Mail did it, but this is definitely a modern technique and of probably something that is very similar to how Royal Mail trained their system. So what they did was they started with lots and lots of data. So one of the problems with training an AI system is you do need lots of data. And in this example is they would need lots of different examples of numbers and letters. And they would do that where, let's say, for example, you take 10,000 examples of the number 8. So, 10,000 different people write the number 8 on a piece of paper, and then you scan it into a computer. And this example here on the right-hand side is just an example of a scanned in number 8. Now, hopefully you can see this over Zoom, but if you sort of look closely, you can hopefully make out the individual pixels here on, if I can show you my pointer. Hopefully you can make out the individual sort of pixels here on the 8. So it's got one here, then one here, then one here, then one here, etc., etc. Now, so once you've got this, you then you go through a process called feature extraction. And this is occasionally one of the difficult parts. And so this is where you have to basically, so at this point here, the machine has no idea that this is number 8. It is just a bunch of random pixels and image data to it. So the point of the feature extraction process is you basically have to tell the machine what part of that image is of interest to you, or what part of that image is the thing that defines what you're looking for. And so in this example here, on the right-hand side of this 8 here now, one example was, and a very basic example is, you would assign a number to each individual pixel in the image based on how bright it was. So for example, pure black would be a 0 value, and pure white would have a value of 255, and anything in the middle would get a number between the two. And hopefully if you look closely, you may just be able to still make out the shape of the 8 on the right. If you can't, here's a bit of a composite image that may make it a little bit clearer, where again, it's the same information, but just overlaid over each other. Now, again, at this point, the computer still has absolutely no idea that this is number 8. It's just a bunch of numbers. It doesn't mean anything to it at all. So the next part of the process is a process called classification. And this is where there are various algorithms out there. I think these are mainly maths-based algorithms that have been around for a long time. One example is it's called a Bayesian classifier. And what you end up doing is you basically feed to the algorithm all these numbers that you've generated here. And it is then able to sort of learn by itself. Well, for example, of all these 10,000 examples of the number 8, we tend to find that these particular pixels here always tend to have a high value, and so for example, these pixels here in the middle have always got a high value, and maybe these pixels here have always got quite a dark value. And if you do that enough time with enough data sets and with enough examples, the idea is that hopefully you're then able to show the machine an example of a letter that it's never ever seen before in its life, and it's then able to compare the result of, it's then able to check the pixels of this symbol A here to all of the other ones that it's been trained on, and hopefully therefore then give you the output that you're after, which in this example is the letter A. Now, that is probably a reasonably basic example of how to teach AI, but it does actually get a little bit more complex. So one of the very classic examples of, or at least in the AI sort of field, is how do you teach a machine to tell the difference between cats and dogs? Now, I would say if I ask any of you the question, you may think it's actually quite a simple process to solve. So you may start describing, well, perhaps a cat has pointy ears, dogs generally have floppy ears, a cat has whiskers, maybe it's got a smaller nose, etc., etc. But what you have to bear in mind is that a computer has absolutely no idea what an ear is, what a nose is, what an eye is, what shapes are, what sizes are. Computers are great at numerical problems, but it's absolutely terrible at understanding those concepts. Now, as humans, we've been learning this since we was born, basically. So we are absolute experts at doing this. And now there are several ways to solve this with a machine learning system. One is a process called edge detection. So if you remember in the previous example, we had to tell the computer basically where the letter was in the image. And so one example with writing a feature extraction system for maybe cats and dogs is there are several algorithms out there that already exist for detecting the edges of an image. So this is effectively where you'd be able to detect a contrast difference between the background and the foreground, and therefore you could almost draw a silhouette around the object to sort of detect where it is in the scene. So here, for example, on the right, where the dog's ear is, you can sort of see an arrow that's been traced around its ear. There's also a little arrow that's going around the dog's eye. And then you may be able to use that with a similar example to the Bayesian system from before and feed it all into a computer. And then perhaps the algorithm is able to almost learn what the generic silhouette shape of a dog looks like versus the silhouette shape of a cat. And you will likely probably get quite good results from this. However, for us at ControlPoint, this wasn't really a solution to our problem. If you take, for example, the contamination photo, which Wez showed earlier. Now, I would argue this is, as a human, we can clearly see that's full of mud and contamination. But if you actually try to sit down to a computer and describe how to understand that as mud, it will be almost impossible. Even detecting shapes and sizes, you may be able to write some sort of algorithm to do that, but the problem with mud and water contamination is it's almost completely random. It would be, I would imagine, entirely impossible to do that. However, this is where deep learning helps, which is the next slide I'm going to go over. So deep learning was developed in around about 2010, and this is described as a subset of machine learning that uses artificial neural networks that enable machines to learn similarly to how humans learn. Now, there's a great quote that I came across from, I think it's a Japanese researcher called Michio Kaku, and he describes the human brain has 100 billion neurons. Each neuron is connected to 10,000 other neurons. Sitting on your shoulders is the most complicated object in the known universe. And this is what we are trying to mimic within a computer, to give the computer almost the Terminator style knowledge of being able to understand anything we throw at it. Now, for a little bit of a biology lesson, on the right, you may be able to see here is an example of a neuron. Now, neurons receive messages from other neurons using the dendrites, which are these little links here. So they receive, in this example here, they receive 10,000 different messages from other neurons. And they almost perform a sort of calculation based on all of that information that's come in. And then they then output their own message along their axons to another, let's say 10,000 odd neurons that they're connected to. And bear in mind, this here is effectively everything that's going off in your head. So hopefully when you're understanding what I'm telling you now, or you look at a photo of a cat or a dog, you'll find that different neurons in your head are activated based on that stimuli and will have different outputs. And that is effectively how a human works in a hopefully a very basic example. And so obviously to try and replicate that in a computer would be brilliant, because this would allow a computer to learn in a huge amount of detail. So some of the benefits of using a deep learning system for teaching a machine are, we don't need to write a feature extraction algorithm. Now, if you remember from before, one of the problems with, for example, contamination was it was very, very difficult to even begin to describe to a machine, to a computer, what contamination looks like. Unfortunately, we don't need to do that. An artificial neural network is able to learn for itself based on patterns that it learns for itself in the images. A good example of this is trying to teach, for example, a baby the difference between a cat and a dog, or to try and teach a baby the difference, or a child the difference between certain shapes like a triangle or a square or a circle. We never really tell them the properties of why they are, why they are what they are. They just kind of learn that themselves through looking at enough examples. And again, this is exactly how we solve the problem here. So this is a very little basic example here. This is a simple artificial neural network that we've mocked up on the right, which has a total of 12 neurons with 3 inputs and 1 output. What does that mean? That means that the network takes 3 inputs from the outside world, it does a whole load of calculations, and then it outputs 1 result. And perhaps an example of that might be if you think about a traffic light. So a traffic light has a red light, an amber light, and a green light. And perhaps we end up passing the status of the red light to this neuron here, e.g. a 0 or a 1, 0 being turned off, 1 being turned on. Then perhaps we do the same thing with the amber light here, and then perhaps the same thing with the green light here. Then all that information gets fed in, a lot of calculations happen, and then we get a result based on what you're looking for. Now, if you remember from the previous example of the biological example, all the lines you can see in these images would be what we know as axons in the human brain. And in this example, there are, hopefully if I've got my maths right, there are 32 different 32 different lines in this little simple drawing. And so when we talk about training an artificial intelligence system, what we're really doing is tweaking all of those 32 different calculations such that when we give it an input, the machine gives us the correct output. Now again, with an example here with only 32, maybe that's something that you could possibly achieve by hand. It's maybe not outside the context of possibility. However, things generally get much more difficult, and generally 32 is a very, very small amount. So I thought maybe a better way to describe this to you would be an example of a sound mixer. So if you imagine that each of the dials is one of the parameters that has to be tweaked, whereby if on the left-hand side is your dog and your cat image. And so let's say you feed the dog's data into this system. Then all of that dog's data has to go through all of these different dials, of which there could be many, many, many thousands. And obviously each dial also has many, many, many possibilities that it could be. And then eventually it goes through all of this system, all of these calculations, and then the system tells us, oh, that was a dog or that was a cat. Now the challenge is making sure that those dials are correctly and perfectly balanced, such that a dog says a dog and a cat says a cat, and maybe a cow says it's not either of these. Now you can see that once you get over 32, trying to therefore manually tweak these numbers would be almost impossible. And this is what the point of deep learning and machine learning and computer generated learning is that it's almost automatically tweaks those numbers for you and learns for itself. So like I said, on the previous slide, we only had 32 axons or 32 lines or calculations to tweak. On the next slide, I'm going to show you an example that somebody else wrote, which is an example of teaching a deep learning network for number recognition. And in this example, it has 826 neurons and therefore 12,960 knobs that needed to be tweaked. It therefore gives you a near infinite amount of combinations, and it's something that no human could really do by hand. So in this example here, the way I'll play it as an animation in a second, but just to describe how it works beforehand. You take an input, so for example, the number 7 that's been drawn on a sheet of paper and scanned in, and then it takes each of the individual pixels, of which there are 784, and it copies, for example, the first pixel to this first neuron here, the first input neuron, and then the second one to the second one, the third one to the third one, etc., etc., etc. And then from there, the machine performs its calculations and hopefully at the end will output the correct result based on everything that is calculated. Now, when I play the animation, you'll see that certain neurons highlight more brightly than others in certain scenarios. And that's because they are more highly activated, which means they are more closely associated to that particular input. And you'll hopefully see the difference between, for example, when I play it now, you see that with number 7, these are all the ones that activate, and they activate, and then it predicts it's a 7. Whereas with the number 2, you'll see that different neurons have activated. Now, some of the same neurons from the 7 may have activated, but there'll be some that are different. And fundamentally, this is also happening in your brain right now. When you look at that number 2 at the top left, your brain is performing some very, very, very similar calculations to derive at the correct result. So that's basically it for my part of the process so far. I'll just pass it back to Wes to carry on with the next slide.
Okay, so in terms of camera. Can everyone hear me or not?
Yeah, I can hear you.
Can everyone hear me or have I gone quiet?
No, you're okay, Wes.
All right, cool, sound. I think we just caught a lead, apologies. So in terms of where you start with AI, when we first went through the process, I think the best way it was described, and maybe the sayings have been used many times before, but if you're going to pick up an elephant, which is effectively what Andy's just described, this is going to be in terms of it's never seen a joint before. Now we're going to try and teach it if that joint is clamped, scraped or clean. You eat it one bite at a time. You teach an infant in the same way that you teach them how to safely cross the road. They don't really need to know lots of controls to begin with, but they know that it must be clear, or a red man must be flashing if they don't cross, or a green man can flash if they can. And then we focus around the visual identification of the issues in the photograph that you can see. But ultimately, we decided we would develop this in-house. We didn't use access to any NIA funding from the gas networks or any funding from the water sector. We chose to take this brave journey alone because we know the potential that this has for changing the way that any network or asset owner can approach quality. We built a team that was passionate. There's nobody more passionate than the team of Andy and Fariba and Kin, who have all been responsible for developing this. And we remembered that we had a goal. We wanted something that was instant. So it was no good if we take the photographs and it takes a week. And the main thing that you've got to do with any innovation-based project or something that's really pushing the boundaries of what's been done before is being brave and not giving up. So what I'm going to show you is a little video of how this now goes, and Andy will actually talk us through the video if there's bits that I miss. So I'm going to show you the video the first time. So this is effectively the joint, as you can see on the screen. You'll be able to see that it hasn't been scraped because the writing runs through the actual pipe itself. We've got the coupler, we've got the leads attached, and we know that we're connected to the paired to the phone through the box. So what you'll see is, as we showed on the video, we smart scan the fitting. That's the first step. That helps the AI have a fighting chance to work out what type of fitting it is. We then again take the photos from the left, the right, and the primary position. And then what the app will do is, once we send those photos to the server, you can see in the large screen, it has identified that that was not scraped and was not clamped. It will then allow the operative to correct the issue. So you can see we've now scraped the pipe. The AI will check, but it now knows that it is scraped, but it isn't clamped. So then the operative would place a clamp in position. You would repeat the process, take your photographs to evidence that you've got a clamp. And this time when it checks, it would allow the box to weld. So from a simplicity perspective, I'm going to show you that one more time. So if you see the picture on the screen, that is unclamped, unscraped, but it is clean. The AI in the real time that you see in the phone that's displayed on the right hand side of this video is able to determine that that is either clamped or not cleaned or not scraped in the time that we're showing you. So we haven't fabricated this. The only thing we've sped up is Andy's hands taking the photograph because it's not exactly the most exciting part of the process. So as I say, scan the fitting, collect all the traceability data, and it tells the Electrofusion box what fitting it is and how long it should be welded for. You take the photographs to evidence how you've prepared it. And then the AI will then inspect those photographs within a matter of seconds to say whether or not it meets the 3 baseline requirements. You can then either rectify the situation or you can prevent the box from welding if they don't rectify it. This time they've scraped it and the AI knows that now it is scraped, but it's not clamped. You would then clamp it. So let's say you've left a clamp in the back of the van. You try to get this to weld without a clamp. If the client doesn't want that to happen, which we would hope many wouldn't, the AI box will prevent the weld from taking place. That is a really simple video that takes less than a minute that shows what Andy and the team have spent the best part of 3 years developing. Would I encourage anybody to have a go? No. What do you need? A massive database behind you in order to keep showing it variations and different pictures over and over and over again. In terms of what is it doing, these are original pictures that Andy gave to me in the early days. Do you want to cover off some of this, or do you want me to cover it? Okay, cool.
Give it both.
All right, Sam. So in terms of, in a very simple world, when the AI looks at that photograph in the top right, it effectively starts to draw a box around what it believes looks like a clamp, based on us showing it thousands and thousands of pictures of clamps. So it knows it's a coupler, so it knows where it expects the clamp to be. It can recognize that there's pipe, it can recognize there's a fitting, it can recognize that there's leads present, and it can recognize the shape and the profile. But there are thousands of variations of clamps. It's one of the challenges we have, is there'll be many people on this call who are manufacturers of said equipment. There's a variety. So you've got to teach it that not every clamp looks the same. In terms of the scraping, mechanical scraping, which is pretty much used throughout the water sector, is much more uniform and harder to do wrong, in our opinion, than hand scraping, especially with the larger diameters. Hand scraping varies as a result of the human operator, depending on how much force they apply to scrape the polymer off. It also varies. If I was to scrape 10 pieces of pipe myself, I would imagine each one of those 10 would be different. It's not truly right first time until we start to use some of the AI side of it, because we've got to teach it to tell us what it's learned, and then we have to keep reteaching it. We've done this in real world conditions. One of the flaws could have been if we'd taught this based on photographs taken in the lab, because then it would have never have learned what an excavation looked like and how to differentiate a very uneven, very interesting background from what we showed in the video, Andy doing it on a white piece of paper. And what we also have to overcome is the human interface with the system, so that we can work out exactly what's happening in terms of how does it talk to an operator, because it's never met one. It doesn't know whether you're in a good or bad mood. So we've got lots of things where we have to do in order to work out what it can and can't do. It's got to be easy to use. It's got to give the facility that if they can't clamp, that they can either request an override code or they can do something slightly differently. And this is 3 slides now of the examples of what the AI has done on its own method. So where it's got the box around it, that isn't something that Andy or I or the team have drawn. This is actually what the AI has drawn around it. It's looked at that photograph and it's seen enough difference in the color of pixels and the shapes that they produce in order for it to say, I believe there's a clamp present in that area. And you can see it'll work on, I think that's a 63mm coupler. And then you can see it'll work on a service offtake reducer. And you can probably see it better on the one on the right-hand side, but it is actually 99.9% confident that that in the picture is a clamp. It doesn't care that it's a clamp. It just recognizes that that's what a clamp looks like. In this image, we're looking at scraping. Scraping is obviously down a bit more challenging because there's less of it usually visible in the picture, but it's been able to detect on that coupler where it's been mechanically scraped. It can even see through the scraping between a service offtake on a high flow top tee and a coupler, even though it's covered in yellow pen because of how it's looking at the images itself. And again, you've got another example on the right hand side where you haven't got a change in color. It's black coupler on black pipe, and yet it's still able to determine that that is scraped. You can see, interestingly enough though, on the left-hand side, it's only 94% confident, which is pretty high that it's scraped. But on the right-hand side, due to how the image is taken, probably light levels and how the pixels relate, it's 98.9% confident. The exciting one as well is cleanliness. Cleanliness is a big factor in electrofusion joint failure. And effectively what we see is the system is able to detect the most common forms of dirt, dust, and water. The one that always interests me is the one in the middle. The computer has drawn a very, very, very small square around the key area for concern, which is between the fitting edge and the fusion zone. And it is 95% confident that that joint is wet. We can obviously see it as a human, but we know what we're looking for. But a machine that Andy, Kin and Fariba have taught has got the ability, which still blows my mind, to work out that those little droplets of water are something that shouldn't be present in the photograph. And again, the final picture shows the level of confidence in terms of where it sits based on the photographic images that we've got. Should you use that data, what you would see as a user of the system is you would see one single set of tick boxes. I've done it as 3 years so you can see how it works. You would see in the first image it can't see all of the clamps. It's not certain it is fully clamped because it's a coupler. It can see it was scraped on that side and you can see it's clean. It then continues to check each one of the images. If you take 5 photographs, it'll check the 5 photographs. So there is a way of working through it should you not be the best at taking photographs. In terms of trials, and the reason that we won the award is, I'm not here today telling you about something that doesn't exist, something that's lovely that might come in another 3 or 4 years' time. I'm telling you about something that does exist, that is used by certain clients at the moment. We did initial trials with J.M. Bentley and Yorkshire Water to test really, not did the technology work, but to test the human interface, to test how it performs in areas of lower signal. We don't need 5G for the AI to run. We were focusing on a live element. So we have a system that allows, if the AI detects something that it's not happy with, if the client wishes, they can actually send that to a human inspector. The human inspector can then check, and then they can allow the box to proceed. One thing we would always say is it'll never be 100%. The same as you'll probably never 100% what type of dog or breed it is. You'll kind of know it's a dog, but you'll never be 100% certain because there's so many different variables. But it will be certainly confident enough to help you make the right decisions. And that's why we were super proud to physically win the award for the best onshore pipeline technology award. We're kind of coming towards the end now, just mindful of time as well. So what did we deliver? I say we, I've done my bit in terms of getting it trialed outside, but really it's down to the guys internally here. We've delivered, and we always laugh when we add the word world in front of it, because if you are the first to do it, likely you are the first in the world. We have delivered the world's first artificial intelligence inspection system for EF jointing. We believe that this is going to create probably one of the biggest seismic changes about how you embed quality assurance into new built networks, whether that be gas or water. It's going to really drive a right first time mentality, not just for the asset owners, but the people in the field. So the people that are actually going to use this app will get real-time interaction. It's operator friendly. We're sure of that now. We've tried it with enough people. It's an opportunity for networks to address the issue around leakage on gas and water pipes. And it allows you, if you are already focused on quality, to target that last 10% of uncertainty, as well as catching a behemoth of data from where it was laid, the location of it, the type of fitting it is, etc., etc. So finally, to conclude, as I said at the beginning, garlic bread is no longer the future, but Electrofusion artificial intelligence inspection is. We're looking now to start to refine the interfaces and controls, and we'll always continue to teach it. You don't stop teaching a child at the age of 5. We want it to get better and clever. We hope that this is the type of product that will give mass market appeal. It won't replace human inspection because we are probably some of the world's most fantastic computers, but it will certainly provide you with a safety net from rework. The other thing that we're looking towards now is we've got very good at teaching it to look for things in a photograph. And if you've ever looked at an excavation, there's a lot more going on in that photograph than there is just a jointing of pipes. So we're going to start to teach the system to look at what else is happening in that excavation. So I'd like to thank you for the time that you've extended to us today. I hope it was really interesting for you guys. I'm now going to hand back to Norman to take any questions.
Okay, thank you very much, Wez and Andy. A really interesting presentation, and yeah, certainly provides some information for or new technology for our industry. We've probably got time just for a couple of questions. Sorry, I'm just trying to get them up, so let's just see now. So the first ones revolve around how well has the technology been adopted by the industry, and then the second part, which that's from Chris, and then from David Clayton, we've got, apart from financial aspect, what do you see stopping this being rolled out across the gas and water industry? I don't know if you want to...
I suppose it's the old adage of people often believe that joints don't fail, that joints, when they hold a pressure test, will pass. But actually, we're pretty certain with the evidence that we have from normal methodologies that joints do fail early in life. In terms of barriers, we can't think of a sensible barrier for not adopting this methodology. The bit that really needs to be emphasized is, you know, this is a real breakthrough in terms of quality assurance. The AI actually, you know, ensures that you can only weld good joints, therefore negating any concerns around you ever doing a bad job. It physically won't let you. So we're hoping that there'll be quite a lot of appetite for this kind of approach. And commercials is something we want to look at naturally, but it's like any puzzle. The more mass market appeal, which we believe this has, that will then in turn bring the AI commercials in line with, you know, with what a network can or can't wish to achieve.
Okay, thanks, thanks, Wes. We've got a go on. Sorry, we've got one final question from Neil Hodgkinson, who says, can I ask how your system identifies the use of type A barrier pipe? Assuming it does, how do you visually inspect the scraping of the pipe when the scraping is only done to the pipe ends, which will not be visible? The external layers of aluminium and external P layers meeting the EF fitting.
It's a good question, Neil, and it's one which I'm going to hold secret within us, but we have methodologies for doing that in terms of photos that can be taken at different stages during the preparation that will allow the AI to learn where it is within that process. So it's, you know, it's always on our radar, is ensuring, as we would do through human inspection, that if a manufacturer says a joint needs to be prepared and assembled in a suitable manner, then we will be able to do that. The other thing that we've got is traceability. If manufacturers start to put traceability barcodes on pipe as well as on fittings, we'll be able to start to capture that data as well.
Right, thanks, Wes. That's all of the questions that we have on the chat. If you have any questions that come to mind, then
drop
please,
me a line. Yeah, drop me a line.
Please forward them to the Guild, and we'll pass them on to Wes and Andy for answers. This webinar has been recorded, so it will appear on the Guild's YouTube channel for you to view at your leisure again. I'd now just like to remind you that we have our next seminar next Tuesday, 13th of October, which is the development consent orders for pipeline nationally significant infrastructure project, given by Mike Gillis of Fisher German and Claire Broderick of Instant News. I'd like to thank Wes and Andy again for their really interesting presentation, and I'd like to thank you all for attending our webinar, and I look forward to hopefully at some point in the future meeting you all in person. So with that, I'll close the webinar for today. Thank you very much.
Thank you. Cheers. Bye.